I'll stand behind Jared.
Okay.
You can stand.
Okay.
I'll do
Um,
like the AT&T Mars.
Did you guys see how we Sprint and T-Mobile sometimes so that it won't be major?
Really?
You did?
Sprint and T-Mobile are combined. So
Sprint and T-Mobile.
Verizon, Sprint and T-Mobile combined with the phones. So it's AT&T.
Sprint Mobile. Sprint has Sprint.
Sprint Mobile.
Okay, first of all, field of an infinite line charge. Okay?
Many towers is surprising. Whatever, I don't know about that.
I used to have T-Mobile. So it's
They're doing pretty good.
I'm going straight off, so,
That's on Verizon.
you know.
It's like the Walmart.
By symmetry, it's uniform and radial from the line.
we
Okay.
get infinite data for 50
Uh, And
copper cord.
perpendicular to the line. Okay? Radial from the line, because if you rotate the line charge, and we're talking about uniformly distributed line charge, infinite uniformly distributed line charge, okay? Then by the uniformity of the distribution, if you reverse the line, you don't change the direction of the field, so the field has to be perpendicular. And also, if you rotate the line charge, that doesn't make any difference in the field, so it always has to be radial. Okay? And again, we did the details, and we're just doing a review here, so we're not going to go through those details. Okay? But by this, cylinder of radius A,
Nelson.
coaxial with the line. Okay? There's no flux through the ends of the cylinder.
We all do.
You have a uniform field in the surface. The field's orthogonal to the surface by the symmetry and everything. Okay? I mean, it's orthogonal to the surface because the line is the axis and the field is perpendicular to the line. So that's a simple consequence just of the geometry of a circle when you come down to it. Okay, so, and I'm being a little sloppy. I could state things with many more conditions, but we're getting the idea. And then you apply them, you review if necessary. So you see exactly what the conditions are and exactly how it works out, but this is the idea, okay? And this is pretty complete, okay? I'm not, again, being real picky on details right now, and you kind of need to be. Okay, well, anyhow, no flux through the ends, etc. So, I forgot. I'm trying to find the cylinder. I didn't bother to say that it has some length, which we call L. Whatever the length is, doesn't matter. It's not going to affect the field. The flux is E times 2 pi r times L. Okay? Okay, and I didn't define lambda, but lambda is the charge per unit length, right? Okay. So I'll append that there. You do have to have the density, but I've kind of defined that here. But you already know what that is. We've already used that. Yeah, again, we're reviewing. So the flux is just four pi k times the enclosed charge being lambda times L, right? So we have two expressions for the flux. We set those two expressions equal, and we see the pi's divide out. 4 is divided by 2 to give you 2. You get E equals here. I used R for the radius because that's what we often use for radius, but I call the radius A. Okay? So you're going to have 2 pi A times L. Well, E times 2 pi AL is this, so the field is this divided by the 2 pi A times L, right? Means the L's go away. You're going to have the pi's divide out, 4 divided by 2 to give you 2. You're going to have the K, and you're going to have the lambda, and you're going to be stuck with an A in the denominator, okay? So, very simple argument, okay? So, unlike a point charge where you have an inverse square relationship between the electric field and the charge, you know, inverse square with the distance, this is an inverse first power, okay? And as we're going to see with a plane charge distribution, infinite plane distribution, there's no change. It's you could say it's the inverse zeroth power. Go from the second power to the first power to the zeroth power, which is just not there. Okay, just 1. Okay? So we'll do that.